This lecture will discuss about emitter follower. Emitter follower, what is emitter follower? Emitter follower is the transistor in which emitter follows the base. Students, do you remember which configuration it is? Common collector. So we are interested to analyze common collector amplifier here. Do we know that this is a standard circuit of transistor amplifier? And I can tell you, in the same circuit, we can demonstrate, we can express, denote the output voltage for common emitter as well as common collector. If you are taking your output across emitter resistance, it becomes common collector. If I mark my output here, I mean across collector resistance, what it will become? It will become the transistor amplifier for common emitter. So we are discussing here common collector, which is emitter follower. And as we know that this is the exact model for common collector amplifier. Again, there is no need to remember, there is no need to memorize. We know that what is a common collector? Collector remains common, base is input, emitter is output. We can simply write VBC, and what is output current? IE. Then what is next? What is input current? IB. But I will write HICIB, then HRC. What is the output voltage? VEC. And HFC IB plus HOC VEC. See that? This thing we have written. VBC has been written as HICIB. See that? HICIB plus HRC VEC. So I hope you all understand very well the concept of getting hybrid model for common collector amplifier based on these two equations. Let us analyze the common collector amplifier, which is we call as emitter follower. And rather we know that common emitter amplifier is the most popular amplifier because of its high voltage and high current gain. So we'll analyze the common collector amplifier in terms of common emitter parameters. What I want to say is, suppose the first part we know that what is AI. AI we know that minus HFC for common collector, 1 plus HOC. What is RL here? Because beyond output there is a RE. So RE will be treated here as output, load resistance. So we can write minus HFC divided by 1 plus HOC into RE. Now if you want to replace in terms of common emitter, what we can do? HFC is written as, HFC is nothing but minus of 1 plus HFE. And what about HOC? These interrelationships we will separately prove in some other lecture. HOC is equal to HOE. If you replace this, what will be expression for AI? This is 1 plus HFE divided by 1 plus HOE into RL. This is the current gain for common collector amplifier using common emitter hybrid parameters. In doing so, we learn one new important thing. What is that? What is that new thing? You can see in common emitter, when you write the common emitter gain, current gain, in its original term, you find that the gain comes negative. But if you substitute those values in this expression, you will get the expression for current gain to be positive. Voltage and current gain are always negative in common emitter amplifier. Why? Because there is a permanent phase difference between input and output in common emitter amplifier, that is of 180 degree. But that generally does not happen in common collector. In voltage gain will never be negative in common collector amplifier. But to determine voltage gain in common emitter, it will be always negative, which indicates that there is a phase difference between input voltage and output voltage, that is of 180 degree. So let us go to the second part. What is second part? Our second part is, what is the second part? The second part of analysis is, what do we get? We get RI. How do we write the expression? HIC plus HRC AI into RI. We know that HIC is equal to HIE. HRC is always nearly equal to 1. HRC is nearly equal to 1. Therefore, we call it as emitter follower. Emitter voltage always follows the base, which is generally less than this. So the reverse voltage gain is generally less than 1 or equal to 1, nearly equal to 1. HIE, and what is this? AI into RI. We can, if you want to substitute the value of AI, we can substitute here. So this is how we can analyze the common collector amplifier using common emitter parameters. Thirdly, what is that? Third analysis. Third part of analysis is AV. How do we get AV? It is AI RL divided by RI. What we will write? What was the expression for AI? AI was 1 plus HFE, then 1 plus HOERL, which is RE. What about RL? It is again RE. And what is RI? RI is HIE plus AI into R. So in whichever manner you want to write the expression, in that manner you can write the expression for T voltage gain. It is very simply AI RL divided by RI. And RO is determined by 1 upon YO. Fourth one, RO is 1 by YO. And what is YO? YO is HOC minus HFC divided by HIC plus RS. And we know that HOC equal to HOE, which is HFC minus of 1 plus HFE. So if you want to write in common emitter terms, YO is equal to HOE plus 1 plus HFE divided by HIE plus RS. So this completes analysis of common collector amplifier in terms of common emitter hybrid parameters. But in the same analysis, let us complete the simplified model also. I mean the simplified analysis of common collector amplifier also. This was the exact analysis of common collector amplifier. Let us analyze the common collector amplifier using approximate model. We know that what is AI? We have seen 1 plus HFE divided by 1 plus HOE into RL, and we know that HOE RL is less than 0.1. So what is current gain in approximate model? Nearly 1 plus HFE. This is the important thing in common collector amplifier. In common collector amplifier, the current gain is nearly equal to 1 plus HFE. Nearly 1 plus HFE, which is minus HFC, which is nothing but minus HFC. Generally, if you see the standard values of HFC, that is always negative. Standard value of HFC is minus 51. So if you substitute that, that becomes 51. And what is HFE value, standard value? 50. 50 plus 1 is 51. I am talking about general purpose, I mean values of hybrid parameters. So what I mean to say is, current gain for common collector, be it exact model or approximate model, it will never be negative quantity. What about the second one? It is RI. What is the expression? HIC, I am writing directly equal to HIE. What is HRC? Is nearly equal to 1. What is AI? 1 plus HFE. And what is RL? It is RI. And sometimes we write it as 1 plus HFE into RE also. We can write it. Why we can write it? Because 1 plus HFE RE will be always much larger than HIE. So what is approximate value of RI? Using approximate model, 1 plus HFE into RE. What about the third one? Third one is not, I mean, very new concept. It is AI RL divided by RE. So what we can simply put, we can write the expression for AIS, AVS. What will be AV? AV can be written as AI is, what is AI? The expression for AI? 1 plus HFE. RL, it is RE. What about this one? It is 1 plus HFE into RE plus HIE. I am intentionally writing this. If I neglect HIE in comparison with 1 plus HFE into RE, this will be purely equal to 1. I mean current voltage gain will become 1. And if you see, if you substitute complete value of RI here, 1 plus HFE into RE divided by 1 plus HFE into RE plus HIE. What the conclusion you can draw? The conclusion you can draw is these parameters are almost equal. What is more here? This is more, denominator is more by HIE, which is very small value in comparison with this. So what? May it be very small, be it very small, but it makes a difference. What does it make difference? Voltage gain is always less than or equal to 1, and therefore we call this amplifier as, therefore we call this amplifier as emitter follower. This is the only amplifier whose voltage gain is less than or equal to unity. Ideally it is unity, otherwise less than equal to unity. So this is the complete analysis of voltage amplifier, common collector amplifier, complete analysis of emitter follower in terms of common emitter amplifier using exact model as well as approximate model. In this analysis we have also understood why do we call emitter follower common collector amplifier as emitter follower. It is because of this property, its voltage gain is less than or equal to unity. Thank you.